Updated this. All right, so today we're going to talk about these. We're still talking about carbonyl additions. And what's today? This 17, 16, 17. So we're going to talk about Grignard additions. In the video that I sent out, one of the I gave like two mnemonics. It's GAKA, Grignard plus an aldehyde or ketone gives alcohol. And then I gave Grignard plus an ester equals a ketone. All right, this is kind of nuanced because you can also get out an alcohol from an ester too, but it's based on the stoichiometry. Right, so when you add a Grignard ester, let me just, and again, functional groups, working knowledge. So if this is my ester, and I add, let me just add simple Grignard. Right, if I add that Grignard to it, right, I'm going to get out and I'll go through the arrow pushing and stuff when we get to some other examples. If I add that Grignard to it, I'm going to actually get out a ketone if I only add 1 mole. So my product, and I'll go through the arrows and stuff too, but my product is going to look like this, right? So I'm adding in this methyl group from the Grignard. So my product is going to look like this. I need to change that color back. Hold up. All right. So this group here is now here. I don't know why this thing is squeaking. Hopefully the recording, the audio is not that sensitive to pick up the stylus squeaking on the screen, but it probably will. All right. So that's with 1 mole of ester. And then so if I take 1 mole of Grignard added to the ester. So if I take that ketone that I get, right, and I add another mole of the Grignard, what should I get if I add another Grignard? What should I get if I take that ketone and add another Grignard to it? Anybody?
Are you adding another CH3?
Yes. And then I'm going to quench it. So what should I get from that? All right, what do I get if I take a ketone and add a Grignard to it anyway, regardless of where the ketone came from?
Would it be alcohol?
I'll get an alcohol. This is a standard carbonyl addition, right? So let's say if I want to add this in, right? So now my product, let me just put the carbonyl in first. I'm going to get that. Come on, Russell. That. Right. I already have this CH3 attached. And then I just added in this one from here. All right. So with the ester, it's the outcome depends on the stoichiometry. So with the ester plus 1 mole plus 1 mole of Grignard, that's going to give me a ketone. All right. If I have an ester plus 2 moles of Grignard, and that's going to give me an alcohol. So the outcome for the ester is different from a ketone or aldehyde, depending on the stoichiometry. If the ratio is 1-to-1, then I'll get a ketone out. If the ratio of Grignard to ester is 2-to-1, then I'll get out an alcohol, because that Grignard is going to keep attacking the carbonyl. Questions about that? This is probably a case where I need to go in and edit the video that I made several years ago, because again, when you add into an ester, you don't necessarily stop at the ketone if you add another equivalent of Grignard in. So it may be something that I do over the summer, go in and update that stuff. All right, any questions?
No questions.
All right, so let's go back to the examples, and let me know if this format is a little different. So let me know if you need me to slow down, or if you have a question, just interrupt me. Just unmute and interrupt me, because I can't see the chat and I can't see if a hand is up, because I'm running this directly from my iPad. So if you have a question or you need to ask me something, just unmute. All right, so let's go to here. All right, this is an ester. This is the ester functional group. You have a carbonyl, and then attached to that carbonyl on one side, you have what we call an alkoxy group. Right, the oxy part is the oxygen. The alk part is the carbon-containing group. So that's why we call it an alkoxy. And then on the other side, you just have a bond to carbon. That's what distinguishes an ester from a ketone, from an aldehyde, from an amide, from a thioester, all your different carbonyl containing, from a carboxylic acid, all your different carbonyl containing functional groups, right? They all have different substituents attached to the carbonyl group. All right, so let's see what we get from here. So this is 1 mole. And this is also 1 mole. What should I get? What's the expected outcome of this? if I have 1 mole of ester and 1 mole of Grignard.
So are you saying, would you add them? Because if it was just 1 mole, it would be the ketone. But
One
if,
ketone.
yeah,
You're right. So I'm going to get a ketone from this. So let's actually go through the arrows here. We got a lot of room to work. So let's go through the arrows. So what happens in a reaction of a carbonyl and a Grignard? What's the first thing that happens? This doesn't change now. This is no different than what we've already been studying. That's why I'm asking, because I want to see where you are as far as knowing like the mechanism of this reaction. What happens first?
the pi bonds break and you give the electrons to oxygen.
Okay, that's one step. I agree, but that's not spontaneous. It has to be facilitated by something, right? So what's the other part of that forces that pi bond to break?
Like making the new carbon bonds.
So you're going to use the electrons here between carbon and magnesium, right? And then use those electrons to attack. Let me do something right quick. Hold up. So this is what that board in Armstrong, we need to get that up on this level. So this is going to attack here like that, right? That breaking that CO pi bond is not spontaneous. That's a really difficult bond to break. It's a pretty strong bond. So breaking it has to be, you have to have something to facilitate that. And so here it's the attack of the Grignard on that carbonyl. What do we get from that attack? What's the intermediate? Because that's not going to give us the product right away.
So is it the part that's attached to the magnesium is now attached to the carbon?
Yes, that's exactly right. So this is what that's going to look like. Let's draw it out. So we'll have, I'll leave it in blue. No, I'll make it black. So we'll have this doesn't change. That doesn't change. And then I have now oxygen. That's negative. I have the OCH3 that's still here. And then I have a bond now to the vinyl carbon. Right, it's this carbon right here. So that's the carbon that ends up bonded to the carbonyl. Anybody not following it? What's this intermediate called again?
Is it the tetrahedral?
It's a tetra intermediate. Good. And again, I can't stress it enough. It's common. No matter what you add, what nucleophile you add to a carbonyl, you're going to get a tetrahedral intermediate. It doesn't matter what the nucleophile is that you add. All right, so now this is the addition part. Right? But this is not my product. I'm trying to get to the ketone. So I need to eliminate. And when I do that, this is where I lose the OCH3. Right? So I'm going to put the pi bond back here. And then I'm going to lose the OCH3 group. So this is the elimination part. Right? Addition and elimination are the reverse of one another. So I'll get this as my ketone. And I'll zoom back out so you can so you'll have a chance to write it. I'm still going to mark this carbon, right? Plus plus that. Right? So that first ester addition with 1 mole of that Grignard, I'm going to get the same tetrahedral intermediate, and then from that intermediate, it's going to eliminate, and then I'll get the ketone. Right? The ketone itself, what distinguishes this from an ester, because I know somebody's thinking it but not asking it, is that you have a carbonyl, and then on either side of that carbonyl, it's just bonded to carbon. So you got a carbon on this side, and you have a carbon on that side. Yeah, so, and I can't stress this enough either. You need to review your functional groups often. Because even after this class, if you're going to med school, dental school, pharmacy school, vet school, I don't know what, if you have to take a standardized admissions test for vet school, but when you get to the chemistry part, these functional groups are going to be, they're going to be right there waiting on you. So make sure that you commit them to memory. All right. Any questions about, go ahead.
Yeah, I have a question.
Go ahead.
So the whole point of this was to remove the alkoxy group?
Well, that wasn't the goal. The goal was to make this carbon-carbon bond right here. But
yeah, but you had to remove the alkoxy group.
Yes, in the process, we eliminated the alkoxy group in the process of making that bond. Now let's say if I took this reaction and I added another mole. So I've gone to lunch, I come back, I have this in solution. What if I add another mole of that Grignard? If I add another mole, and then add in some HCl after adding in another mole of Grignard, what would I get? And I'm not adding it to the start material, I'm adding it to the ketone product. Because once I set this up and go to lunch and come back, that the flask is going to contain only the ketone. Might be a little bit of ester left, but not much. So you'll have all this ketone floating around in solution. And I come back from lunch and decide I want to convert it into an alcohol. So I add another mole of Grignard. What would that alcohol look like? That doesn't change. Where's the reaction going to take place?
Is it the double bond that's not attached to the oxygen?
That Grignard is not, it won't attack that vinyl group. It's all, the carbonyl is way more polarized. So if I have a ketone plus a Grignard, what should I get out? A Grignard plus an aldehyde or ketone is always going to give me what?
You're gonna make alcohol.
An alcohol, right? That's why I put this part in right here, because I need to quench it. Right, so my alcohol, my final product is going to look like this, right? OH. And I'm just going to have 2 of these vinyl groups attached. I'm going to change the color on this one. And this one was red. Right, that's what that final alcohol would look like if I added 2 equivalents of Grignard to that ester. Questions about that? Any questions about anything? Same mechanism, same arrows. The only difference is instead of attacking the ester in that second part, you're going to attack the ketone. Any questions? All right, let's go back to the examples on the back page. We're not going to do any of the retro synthesis and working backwards. We'll save that for the next section. So let's go back to here. We did this one already. Is that right? And we said the product was an alcohol like that looked like this. Is that right? Then we do that one on Wednesday.
Yes.
And this one.
Yes.
And this was the product where we added in this 4-carbon chain right here. I actually couldn't export the notes from class, so I just rewrote them because I haven't figured out yet how to export those pictures. I'll figure it out though. So hopefully you saw that. All right. Let's do this one right here. Predict the product. That's what it's asking us to do. So what am I starting with? What functional group is this?
Ester.
It's an ester. Okay. That's the key to understanding this problem. Right? It's an ester. And so now remember with the ester, the stoichiometry matters. So now when you look at the stoichiometry, it's a 2-to-1 ratio. Right? Evidenced by this number right here, 2 moles of this Grignard, and then follow that up with an acid. So what am I going to get from this if I add 2 moles of Grignard to that ester and then add some acid later? What am I going to get from that? Right. Hopefully this will stick. All right. Ester plus 2 Grignards. I'm going to abbreviate Grignards. Well, no, I'm not. We'll give you an alcohol. Ester plus 2 Grignards will give you an alcohol. So what is this alcohol going to look like? Anybody? All right. This is my Grignard. Let me ask this question for the Grignard. Which carbon is going to attack the ester? We talked about this on Wednesday.
CH2, so you'll have
Yeah.
2 CH2s on the car, 2 of the Grignards, and then the OCH3 will break off.
Okay. All right. Good. So you're saying that I'm going to have for my product. It's the right. Yeah, that's the right ester. So this is the OH. And I'm going to have 2 of these groups on here, right? Is that what you're saying, Mike?
Yeah.
Okay, great. Right. Both of those groups. No, I need a different color. Both of those groups are added in. And if you want to go through the mechanism, we can do that if it'll help you. And then that'll be that plus MGBR. But of course, this is trash, right? I don't care about that. that is not useful to me at all. So it ends up in the waste. But it helps us to keep track of the atoms and the different things that we lost or gained. Any questions about that? All right. Anybody want to see the arrows for that?
Yes.
Okay, great.
Can you add them in, please?
Yeah, let me let's see if I can do it down here. This is gonna be so little, but we're gonna try it. And take the pencil down some. Okay, so in the first, might not be that bad. To take advantage of all the space on this sheet. So that's my ester. And I'm going to react this with this Grignard. And I'm gonna write out the CH2 so you can see which bond I'm breaking, because it's always the same bond. Right, so this is where your electrons are coming from, the carbon metal bond. Remember, it's polarized towards carbon, right? So the carbon is my nucleophile. That doesn't change. So this is my nucleophile by default. That's my electrophile. So now that this arrow is coming here like that, boom, and I'm breaking the carbon oxygen pi bond. All right, what am I getting from this? Once this reaction happens, what do I get? Anytime a nucleophile attacks a carbonyl, what do I get? Before I get to the product. Is that right? Right, I always get this tetrahedral intermediate. Always. So that's with 1 mole of ester. I'm sorry, 1 mole of Grignard added to the ester. How does that eliminate? Anybody? Or what do I need to do to eliminate OCH3? Let me ask that question. That might be easier to process.
The 2 electrons from the oxygen form a double bond.
So
And
do
then
this.
and the carbon oxygen bond between breaks.
Good. And that's going to give me a what? What functional group?
A ketone.
Ketone. But up top, it said 2 moles of Grignard. Is that right? So then I need to show another addition step, because that second mole of Grignard, I'm gonna make it a different color. Right, and if I have 2 moles of Grignard and 1 mole of ester, that second mole of Grignard is going to attack the ketone that I make from the addition of the first mole. Right, so this is coming here like this. That doesn't change. This doesn't change. Am I going to get another tetrahedral intermediate? From this addition?
Yes.
I am. Right, it's just going to be with a ketone and not an ester. All right, everybody okay with that part? And then, oh, let me put my magnesium in. I don't think I did it over here either. Oh, yes, I did. All right. Now, what's the last thing I need to do with this? To make it into alcohol. That's what the second step is for, right? This step right here. Remember, that's HOAC is an abbreviation for acetic acid. Which is what? If I'm thinking in terms of addition of a Grignard to a carbonyl, what's the role of the acid?
Add hydrogen.
It's a proton source. Good. So I'm gonna add. I'm gonna draw it out so you can see what happens here. So I'm gonna do a proton transfer from here to here. Right. So now my product looks like this. So this is now O. Too many colors. OH. And then is that right? Plus what? What's left over now? Is that right? The OH. Well, let me fix that. And make it match. Yes, no, maybe.
Yes.
Yes.
And then don't forget over here too. Once you eliminate here, then you get this. But it's trash, but I'm gonna show it because I want you to be able to keep track of everything, right? So this is also gonna be that's trash. We don't care. And this is also trash. Right. Any questions about that? The mechanism doesn't change. It's just the different intermediates that you encounter will be different for the ester and for the ketone or aldehyde. All right. And again, another thing that we see here is if I'm working with an ester and I'm taking it all the way to the alcohol, right? It's just like working with a ketone because I'm going to get a tertiary alcohol as the product. That's tiny. It won't be that small in the notes when I upload it. Any questions? All right, let's do the next one. I'm gonna be quiet though, which is weird because we're on Zoom, but you gotta pick up the slack. What is the outcome of this first reaction right here? What do I get? What do I put in this hole right here? I have an aerial halide. Is that right? The aerial is just for this aromatic ring. Of course, the halide is bromine. I have an aryl halide plus magnesium and ether at low temperature. What do I get when I stir those things together?
Magnesium will take the place of bromine.
Good, good, excellent. So I'm going to get a aerial Grignard. Is that right? This is a Grignard synthesis. Right? This is the way to make Grignards. You take a metal, you stir it with an alkyl or aryl or vinyl halide, low temperature, and the metal is magnesium, obviously. But you take that, you stir them together, and you get out a Grignard. All right, now
I have
look
a
at the next
question.
step. Come on.
Why does the magnesium like take the bromine's place?
Well, when you make a Grignard, and with the aerial species, the mechanism may be a little bit different, but you actually donate. Remember when we went through the mechanism for the Grignard synthesis? The magnesium has 2 electrons. 1 electron. Actually, let's just do it here. This is magnesium 0. It's got 2 electrons. It's actually going to donate 1 electron. I'm going to change the color of those because of that crap that's around it. Right? It's going to donate 1 electron this way. And then this bond is going to break homolytically. Right? So I'm going to end up with this radical like this. Highly unstable, but it is what it is. Plus magnesium plus 1 with 1 electron left, plus Br with a full octet and a negative charge. Right? And then the magnesium and the carbon are going to come together. That's how I get that. So it's not really taking its place in a sense of just swapping. You actually have to go through some. This is still positive. This is still negative. Right? So it's like a radical substitution, even though double bonds don't substitute directly. But I'm showing this like I'm showing the initial the mechanism that we studied already.
Okay.
All right. So it's probably a different mechanism for the aerial, but this is just to kind of make it plain because you can't substitute at a sp2 carbon. You can only add then eliminate. Right, but it is a radical process, right? Where you have this one electron transfer. All right, so that's my Grignard. And then what am I doing with this Grignard? I made it. Now what am I doing in the next step? I have, what functional group is this? Working knowledge. It's an aldehyde. That hydrogen gives it away. The hydrogen bonded to the carbonyl, that's characteristic of an aldehyde. So I got that plus a Grignard, and then I'm gonna quench it with some acid. What am I gonna get from that? You have a Grignard plus an aldehyde or a ketone will give you what?
And alcohol.
Alcohol. So from this reaction, I should get an alcohol, whereas the aryl magnesium bond, that where your electrons are coming from. So you're gonna get a new carbon-carbon bond between the aromatic carbon here and the carbonyl carbon here. Right, so that product is gonna look like, that resolution is terrible. That product is gonna look like this. Let me just redraw that. That's crappy. Right, that's my product. And this, again, I have a new carbon-carbon bond between these two. That's the goal, right? Anytime I'm doing a reaction like this, it's to construct a new carbon-carbon bond. And it's a very facile way to do it. So it'll be that plus, let me see, I used HCl, so it'll be Cl, Mg, Br, where chlorine is the conjugate base of the acid. That conjugate base of whatever the acid is always ends up with magnesium. Right? So this is a multi-step synthesis. Right? I could also write this a different way. I can write it and combine all the steps too. So I can write it like this. I could start with this. Sorry for all the squeaking. But I can, come on, Russell. I can start like this. Right? And then over my arrow, number 1 is magnesium at 0 degrees Celsius in ether. Number 2 is that aldehyde. And then number 3 is HCl. I can also write it like that. And it's going to give me the same thing, same outcome. All right, questions about that or that problem? All right, I want you to finish this one on your own. If we were in class, I would just have you work on it. But since we're not, and I don't want to it's pointless to open a breakout room with 7 minutes left. I'm just gonna leave it. And I want you to work on that one on your own. But it's nothing different. If you look at the steps and you look at the reagents, there's nothing new here. And what functional group is this so that you'll be aware of what's going to happen in that second step?
Esther?
It's an ester. Excellent. Right? Good. So now you'll know how to proceed with that step. And then you'll understand what the purpose of the second or the third, well, that'd be third step. The third step is. So this will be step 1. This is step 2. And then it says step 3. And now I'll even give you a hint here. All right. So work on this one. If you get stuck, feel free to email or ask a question, and then, but you shouldn't get stuck. Hopefully you won't get stuck, but things happen. All right. Any questions about anything we talked about today? All right. If not, we're going to stop here. And I'll upload these notes to our Blackboard, and the exam will open in a few minutes, actually. So if you want to take it early and get it over with, you can do that. If you want to wait, you can do that. Just don't wait till 10 o'clock on Sunday. Because if something happens and you email me at 10 on Sunday, I probably won't respond. Being honest, keeping it a buck.